We're going to cover some of the basics that you need to get started with deep learning. That includes some math, like linear algebra and calculus. It also includes some programming. Specifically, we'll be using NumPy, which is a Python library for working with arrays. If you're familiar with these concepts, feel free to skip this lesson and jump to the next one. We'll start with the basics of linear algebra. And at a really fundamental level, linear algebra is about manipulating and combining vectors. And a vector is a mathematical construct, but it looks a lot like a Python list. So we can define our vector v using a math formula, and it has two elements, 0 and 1. And what we say is our vector is a one-dimensional array, because data is only going in one direction. And we'll talk a little bit more about that in just a second. But first, let's go ahead and create our vector in NumPy. And what we can say is our vector is a NumPy array. And I changed the first element to a 1 because we're going to use this vector later. But we can see that we've created our vector using NumPy. So 1, 1. Now we can go ahead and create what's called a two-dimensional array, or a matrix. So in this case, the first row of the matrix is the same as our vector, and the second row of the matrix is different. So we can see this matrix has 2 rows and 2 columns. And we call it two-dimensional because it has rows and columns. If you wanted to get a single value in our matrix, you would need to specify both the row and the column that the value belongs to. Whereas in our vector, if we want to get one number, we only need to provide one index to get that number. So that's why we call our vector one-dimensional and a matrix two-dimensional. All right, before we get more into dimensions, let's actually jump back into vectors and plot our vector. So we can import matplotlib.pyplot as PLT, and then we can set the limits of our plot, which will basically control our x values that are shown and our y values that are shown on the axis. So our x and y values will be from 0 to 3. And then we can plot our vector. So by convention, vectors are plotted from the origin. So we're basically saying draw a vector that goes from the origin of the graph, 0, 0, to the point that we defined, 1, 1. And then we're just going to specify a couple of parameters that control how big the arrow is. And we can go ahead and plot it. All right, so you see that we end up with an arrow that goes from 0, 0 to 1, 1 on our graph. And then it points in a direction, right? It points up and to the right. And what we say is a vector has a length and a direction, and the arrow points in the direction of the vector. All right, so to talk a little bit more about the length of the vector is also called a norm. And the most commonly used norm is the L2 norm, which is the square root of the squared lengths of the vector. So the formula for the L2 norm looks like this. So it's basically saying take each number in the vector, square it, add them all together, and then take the square root. And that gives you the L2 norm, or Euclidean distance, which is the most commonly used way to find the length of a vector. And we can implement this in NumPy as well. So we implement the square root on top of the sum of v squared. And this gives us the square root of 2, which is the length of our vector. All right, so this is graphing a vector in a two-dimensional space. So array dimension is different from vector dimension. This dimension of a vector space is how many elements are in the vector. So in this case, we have a vector with 2 elements, and you can think about that as graphing an x-coordinate and a y-coordinate. But if we have a vector with 3 elements, we then need to graph an additional dimension. So let's see how that looks. We'll go ahead and graph a vector with 3 elements. So this vector has 0, 1, and 1 as elements. And we can do a little 3D plot. I'm going to copy some of the code here because it duplicates what we already did. But we first create a 3D subplot, and then we are going to graph our vector on the 3D subplot. And you can see what this looks like in 3D space. So our arrow is pointing in a direction in 3D space. And if we had more than 3 elements in the vector, we would essentially have our vector be in a space that is that many dimensions. So for example, if we had a vector with 5 elements, we would say that our vector is in 5-dimensional space. And when we're working in deep learning, we may work with vectors that have thousands or tens of thousands of elements. So we're working in very, very high dimensional space. And obviously we can't really visualize and graph those vectors. So you have to think about it a little bit abstractly. All right. Now, when we index our vector, we're indexing each element in the vector or each dimension separately. So let's say that we have our vector v. If we wanted to get the first element in the vector, we would do v0. The second element would be v1 and v2 and so on. So if we want to get each element of the vector, we index it like this. v3. All right. Now, one really, really important thing in linear algebra is how we manipulate vectors. So how we scale them and how we combine them. So what we can do is we can take our vector, let's take a vector 1, 1, and we can scale it by a single number, 0.5, which means that every number in the vector is multiplied by that constant. So that's v. So that gives us 0.5 and 0.5. So that's our scaled vector. We've multiplied it by our scalar number, which is 0.5. And we can graph out what our new vector looks like. So this is the new vector, 0.5, 0.5, and it's been scaled. It's the original vector, but it's been scaled by our scalar. So you can see that it now ends at 0.5, 0.5. We can also add vectors together. So we can say, for example, v equals numpy.array 1, 1 plus numpy.array 1, 0. And this results in 2, 1. So the element at position 0 in each vector is added together, and the element at position 1 at each vector is also added together. And if you have more elements in your vector, it'll basically take each element and add it with its corresponding element in the other vector. So this will give you another 2 at the end. All right, I'll get rid of this. And then we can go ahead and plot this vector 2, 1 to see what this looks like. All right, so we see it has a shallower angle than our earlier vector, but it is pointing up and to the right still. All right, so when we work with our normal Euclidean 2D coordinate system, 0, 1 and 1, 0 are called our basis vectors. And the reason for this is you can reach any point in 2D Euclidean space using these two vectors. So let's graph these two vectors, and then we'll talk a little bit more about what it means to be a basis vector. So here's v1 and v2, and we can go ahead and set our axis limits, and then we can use plt.quiver to actually go ahead and plot out our vectors. So we can see what these two vectors look like. One is essentially going up on the x-axis 1 unit, the other is going right on the y-axis 1 unit. So using these two vectors, we can reach any point in 2D Euclidean space. So for example, let's say I want to reach 0.31. I want to reach this point. So what I could do is I could do v1 plus v2 times 0.3. And that gives me 0.31 as my new vector. If I wanted to reach, for example, 5, 1, I would do 5 times v2 plus v1. There you go. So you can essentially reach any point using these two basis vectors. And what we say is these two basis vectors are orthogonal to each other. And the reason we say that is when we take the dot product of these two vectors, we end up with 0. And a dot product is basically taking each element in the vector and multiplying it by the corresponding element in the other vector. So we're taking 0 and multiplying it by 1, which gives us 0. Then we're taking 1 and multiplying it by 0, which also gives us 0. So our dot product ends up being 0. And what that dot product means is that none of vector 1 overlaps with the direction of vector 2. Right? They're going in completely perpendicular directions where there's no overlap in the direction that each one is pointing. Now, if they were instead like this, if v1 was 0, 1, and v2 was 0.1, or even 0.1.1, the direction would overlap. And let's graph that out and see what that looks like. Let me make this a little bit longer. So you can see that there's now some overlap in the x direction of both vectors, right? They both point in the y direction, straight up, some amount. So if they're orthogonal, they're perpendicular. If they're not perpendicular, then they're not orthogonal. All right, so the last piece of linear algebra basics I'll tell you about is what's called a basis change. So in 2D Euclidean space, these are our two canonical basis vectors, the basis vectors that we use to define our coordinate system. So if we have a coordinate 2, 1, it's really just defined in terms of these basis vectors. What we're saying is, let me actually do this in terms of our vectors here. So let's say we have 0, 1 and 1, 0 as our basis vectors, and then we have a coordinate 2, 1. I would have to reverse these. 1, 0, 0, 1. And we have a coordinate 2, 1. So 2, 1 would be 2 times v1 plus 1 times v2. So that's what our coordinate is telling us. It's telling us how many of each basis vector we need to add together to get our final point in Euclidean space. So all coordinates, so if your coordinate is 5, 5, 10, 10, it's expressed in terms of these basis vectors. Now, one thing you can do is you can change the basis of a coordinate. So for example, we could define a new coordinate system where the basis is 1, negative 1, and let's say 2.5. These could be our new basis vectors, and we could change the basis of our coordinate to the new set of basis vectors, which would mean we would have to express our coordinate 2, 1 in terms of these basis vectors. So I'm not going to talk about how to do a basis change, but if you want to read more, there are books and resources that you can dive into to learn more about this. But a basis change is a very common operation in machine learning and deep learning. So it's an important concept, and it's important to know what it is and that it's possible, but we're not going to get into the specifics of how to do it. All right. We touched on matrices a little bit before. We can actually arrange vectors into matrices. So let's say that we want to define a matrix M. And usually when we're defining a matrix, we write it in uppercase, both in math formulas and in code. It's just a convention. So we can say that our matrix has 3 rows. So let's say it's 0, 1, 2, 1, 0, 2, and 2, 1, 0. So we can think of each row as a separate vector that we've arranged into this matrix. So we have 3 different vectors. Each vector is 3-dimensional that we've arranged into this matrix. And we say, again, remember that a matrix is a 2-dimensional array, which is different. I know it's confusing, but it's different from the dimension of a vector space. Okay, so we can check the shape of our matrix M, and we see that it has 3 rows and 3 columns. And this tells you a little bit more clearly that it is 2-dimensional because it has both rows and columns. So you need 2 numbers to index if you want to get a single value from our matrix. And we can index our matrix similarly to how we indexed a vector, but we now need to pass in two numbers. So if we want to get the first element, the top left element in the matrix, we do M00, 0. We can also select entire rows and columns at once. So we can do M0. This just gets the first row. We could do M:0. This gets the first column, which in this case is identical to the first row. Let me actually change this, and we can see a little more clearly that the first column is 0, 1, 3. And we can also get slices of the matrix. So what this does is it gets the upper left corner of the matrix, the 4 elements in that upper left corner. We can also use indexing to assign values. So we can assign 10 to the top left corner of the matrix, which will now look like this. All right, so those are a few of the basics of matrices and vectors, but let's actually dive into a concrete example now to build some more intuition and pull all of this together. Teaching or learning about things abstractly can be hard. So what we're going to do is we're going to apply linear regression to actually predict tomorrow's temperature. And to do that, we can use the linear regression formula. So that formula is just this. So basically this is saying y hat, which is the predicted y, which is tomorrow's temperature, is w, which is a weight value or coefficient, times our x value plus b. So this is the linear regression formula. And I'll talk a little bit more about what w and b are in just a second. But first, let's go ahead and read in our data and take a look at it. So we're going to go ahead and import pandas. Then we're going to read in a file called clean weather. So this is weather observations. And then we're going to fill in missing values in the data. And then we can take a look at our first 5 rows. All right, so our data is actually daily weather observations. So each row is a separate day, and the columns contain information about the weather that day. So Tmax is the maximum temperature that day, Tmin is the minimum temperature, and Tmax tomorrow is tomorrow's temperature. All right, so what we're going to do is we're going to use Tmax, Tmin, and rain to predict Tmax tomorrow. So we can actually expand our equation, the typical linear regression equation, to include 3 different x values. So in this equation, x1 is Tmax, x2 is Tmin, and x3 is rain. And then we add them all together, multiply them by the weights, add the bias, and we get our predicted y. So for example, let's say W1 equals 0.7, W2 equals 0.3, W3 equals 0.1, B equals 10. Then if we wanted to predict tomorrow's temperature for the first row, we would do W1 times 60 plus W2 times 35 plus W3 times 0. And then we would add in 10. And that would give us our prediction for tomorrow's temperature, 62.5. So we would use this equation whenever we want to make a prediction. Now, what you may notice by looking at this is we're actually multiplying 2 vectors together. So we can think of w and x as separate vectors. So we can define this using NumPy. So we can say our w vector is this, and our x vector is this. And then we can do numpy.dot wx. All right, so what this does is actually this part of the equation. It's the exact same as W1 times 60. Actually, let me just change the numbers here so it all adds up. So it's doing this part of the equation. So we end up with the value, except it's 10 lower than what we got before because we didn't add in the bias. So we would just want to add in the bias here, and then we would end up with the same result as before. So dot is the dot product of two vectors. So it takes each element in the first vector, multiplies it by the corresponding element in the second vector, and then adds them all up. All right. So this can save us a lot of time, right? We don't have to write out all of the individual x values when we want to multiply, but it's not perfect. What if we want to make predictions for multiple rows? It would get really annoying to have to write out the dot product for each row separately. Luckily, we can actually use matrix multiplication to help us with this. So here's the equation for matrix multiplication. So if we're multiplying two matrices A and B, this is what it looks like. You multiply across each row in A, and you multiply down each column in B to get your results. And your results will have the same number of rows as A and the same number of columns as B. So here's a little GIF to visualize what a matrix multiplication looks like. So we take the column in B and we multiply it by each row in A, and then we add the results together to get our final result. So let's watch this one more time. All right, so that's matrix multiplication. And let's look at a couple of examples. So we'll pull the first three rows of x out into its own NumPy array. All right, so this is the same data we looked at before. It's just now in array form. And then we can take a look at our weights. So we defined a weight vector before. So let's take a look at our shape of our x matrix, and we see it's a 3 by 3 matrix. We can take a look at our w vector. We see it's one-dimensional. So it only has values going in one direction because it's a vector. So we actually need to go ahead and convert this to a matrix to do matrix multiplication. So what we'll say is the matrix W equals the vector W reshaped to have 3 rows and 1 column. So that's what the NumPy reshape method does. It changes a vector or a matrix or any NumPy array into a different NumPy array, provided that the arguments you pass into shape have the same number of elements as the original array. So in this case, we take a look at W. It's now a matrix with 3 rows and 1 column. And we can take a look at w.shape just to confirm that. All right, we can now multiply with the @ symbol x and w. So this gives us our results without the bias. Then we can go ahead and add in the bias. We'll first turn the bias into a vector, and then we'll add the bias in to x times w. So this gives us the same results as when we did vector multiplication and when we did the manual formula. But it's just one operation. It's way, way easier to write out, and it computes much faster on a GPU or CPU as well. All right. So far we've been using values for W and B that I gave you. We can actually calculate these values as well directly. So in the next lesson, we'll learn a technique called gradient descent that we can use to calculate the values. Another way is to use a method called the normal equation method. So the equation is W equals x transpose times x inverse times x transpose times y. So I'll talk about the transpose and the inverse in just a second, but this is the equation that gives us our W coefficients. And basically what it's doing is it's finding the coefficients that project y onto the basis x with as little difference between the predictions and the actual values as possible. All right, so another way to say that is when we multiply x by w, it should give us the least difference between the x times w values, the predictions, and the actual y values as possible. Okay, another way to say this is that we're changing the basis vectors of y to x. So the coefficients W give us the mapping between the current basis of y and the new basis x with as little loss as possible. So it's a very complicated concept. If you want to understand more about this, about basis changes and the normal equation, I really recommend the Mathematics for Machine Learning book. But if it's not super clear, you don't need to worry too much about it. This equation is not something that we'll be using in the next few lessons. It's just something that I'm using to illustrate a few key linear algebra concepts. But the thing to know here is we are projecting y onto the basis x. And we're trying to find the best prediction given that basis change that approximates y as closely as possible. Okay, so there are a few things here that we're going to look into in a little bit more detail. So the first is this term that looks like xt. So it looks like this. This is known as a matrix transposition. So it's when we swap the columns and rows in a matrix. So if we take the transpose of our weight matrix, it actually turns into a 1 by 3 matrix. Before it was a 3 by 1 matrix. And it's now a single column. So before it was 3 separate rows, now it's 1 row with 3 columns. And we can multiply this by the transpose of x and add in b. And then we'll get the same results as before, except now they're all in 1 column. So if we wanted to get the original format, we'd have to do another transpose, which would give us our results like this. So a transposition swaps the rows and columns of a matrix. We can take a look at the transpose of x to see what that looks like. So each column becomes its own row, and vice versa. We use this a lot in various operations in deep learning, so an important one to understand. Okay, we can also use the NumPy all close function to verify that our new multiplication and our original multiplication do the same thing. And that just looks like this. So the NumPy all close function is used because in really any computer, when you're multiplying floating point numbers, you can get small errors with rounding. So I'll show you what that looks like. Actually, we don't see that here. But on your computer, you may see a bunch of decimal points and a very small number, like a 1 at the end. Those numbers are actually the same. So for example, you might see 52.500001. That's the same as 52.5. It's just when the computer actually multiplies the matrices out, it has a small error with the numerical precision. And you'll see that a lot in deep learning when you're multiplying matrices. So all close basically checks, is this close enough that they're actually the same number, even if they're actually a little bit different? Okay, the other thing that you looked at that may not have been clear is matrix inversion. So that looks like this. It is a matrix with the -1 sign above it. So a matrix that's inverted is similar to a number that's inverted. So the inverse of 4, for example, is 1/4. And when you multiply 4 by 1/4, we end up with 1. The inverse of a matrix is the same thing. When we invert a matrix and multiply it by the original matrix, we end up with the identity matrix, which is 0 everywhere and 1 on the diagonal. So this is known as the identity matrix. And this specifically is a 3 by 3 identity matrix. We could also have a 2 by 2 identity matrix, 4 by 4, etc. But identity matrices are always square matrices. They have the same number of rows and columns. All right, so we can try to invert our X matrix using the linalg.inv function of NumPy, and we get an error that X is a singular matrix and we can't invert it. So a singular matrix means that some of the rows and columns are linear combinations of the other rows and columns. So earlier when we added our vectors together, so if we have numpy.array 1, 1, a linear combination of this would be multiplying it by 0.5. So 0.5, 0.5 is a linear combination of 1, 1 because it's just the vector 1, 1 multiplied by some number. Adding two vectors together is also a linear combination of those vectors. So that ends up with 1, 2. So a matrix being singular means that some rows and columns are linear combinations of other rows and columns. And the reason we can't invert a matrix in that case is because one dimension has its area as 0 in that case. And the formula for inverse, at one point in the formula, there's a term that says 1 over area. So if area is 0, then you're taking 1 divided by 0, which is undefined, which makes the inverse of a singular matrix also undefined. We can correct this using a technique called ridge regression, which essentially forces each row to be unique and not a linear combination of other rows. And the way we do this is we add a small ridge to the diagonal. So we can invert this matrix. So what is this matrix? It's the same matrix X, but this time we've added 0.1 to every element on the diagonal of the matrix. And this forces each row to not be a linear combination of other rows and each column to not be a linear combination of other columns. If you see, we've changed it from 60 to 60.1. So now that 0.1 is actually a unique value in that row and column. And same thing in the other rows and columns. All right, so now what we can do is we can go ahead and take the inverse of the ridge regression matrix, which we saw up here. We got this inverse. So we can say inverse, and then we can multiply that by our original X. So I have to update this. All right, so we add a small value to the diagonal of our X matrix, and we're going to call this our ridge matrix. Then we take the inverse of our ridge matrix, then we multiply the ridge matrix by the inverse. And you can see we end up with the identity matrix. And this is what I was talking about earlier when I mentioned the small numerical errors you can get. So what we can do is we can check numpy.allClose, ridge at inverse, and the 3x3 identity matrix. And we can see that these are in fact equivalent. Okay, so we can now use that normal equation that I showed you before to solve for W. So we'll first pull the Y values out of our data. So we'll say Y equals tomorrow's temperature from the first 3 rows. And then we can say W equals np.linalg.inverse x.t at x, and then we'll add in the small ridge to fix our numerical issues. So we take the inverse and then we multiply that by the transpose of x and we multiply that by y. And then we end up with our weights. So these are our weights. And then we can multiply x by our weights to get our predictions. So these are our predicted values for tomorrow's temperature, and these are the actual values for tomorrow's temperature. So you can see they're pretty close. They're pretty close because we made predictions on the same data we trained as, and it was very little data. So we essentially overfit to our very small training set. But we'll talk a little bit more about overfitting later if you're not familiar. Okay, we left B out of this calculation because it's not super important for us to know this formula by heart. I was mostly using the formula to illustrate some linear algebra concepts. But if you do want to dig more into the normal equation, you can learn how to also use it to calculate B. Okay, now just a couple more concepts to go. The first thing I want to talk about is broadcasting. So we did broadcasting earlier when we took our B array, which was just 10, and we added it to x times w. So let me show you what this looks like. So we'll say b equals that, and then we can add in b here. And we can see that b has been added to each row in our predictions. So each row has had 10 added to it. And this is known as broadcasting. So two arrays can be broadcasted if their shapes are compatible. And if their shapes are compatible, one of two things has to be true. So one of these has to be true. Either the smaller array has to be of length 1 in dimensions that don't match, that don't have their lengths match, or the smaller array has to have dimensions exactly matching the larger array. So for example, if these are the shapes of two arrays, you could broadcast these two shapes. Let me actually simplify it. So this 2 would essentially be added to every row if this was a vector shape. On the other hand, if you had something like this, these could not be broadcasted. And I'll show you a couple of examples of things that can be broadcasted and things that can't. So in this case, you can broadcast these two. So we first initialize a 5x1 matrix with all ones. That's the numpy.ones function. And then we add in a 1-element vector, or 1-element matrix that's of shape 1, 1. So this will add 1 to each element in matrix A. This also works. This is just adding a vector. So it's initializing a vector with shape 1 and adding that vector to each row. This will cause an error because the shapes don't match. So the shape of A is 5, 1. So what we add to it has to have either shapes that match A or 1 in the dimensions that aren't matching. You can also multiply using broadcasting. So numpy.full is here we're initializing a 1x1 matrix where the value is 2. So numpy.full, you pass in a shape and then you pass in a value, and it initializes an array of that shape filled with that value. So here we're multiplying every element in A by 2. All right, and then we have numpy.random.rand, which generates random numbers between 0 and 1 in a given shape. So this will generate a 5x1 matrix with random numbers between 0 and 1, and we can multiply that by A, and we get our result. Okay, so that's broadcasting. The last concept we're going to cover is derivatives. And I'm going to cover this at a pretty high level because we get much, much deeper into derivatives later on. But let's say we have a function x squared. So y equals x squared. So the derivative of this function is 2x. And the derivative is the slope of the function, or how quickly the function is changing. Put a couple more dollar signs here. All right. So what does that mean? What that means is 2x tells us if we add 1 to x, approximately how much will y change. All right. So to show you how this works, let's first import matplotlib, and let's plot out our x and our y values for y equals x squared. So these are our x values. We're creating a range from -10 to 10, and we're stepping by 0.1. So we'll have -10, -9.9, etc. Then we're going to generate our y values by squaring our x values. And then we're going to plot our x's and our y's. And we see we end up with a curve. So when x is 0, y is also 0. 0 squared is 0. But as we move away from 0, our y values get higher and higher. And they get higher and higher faster and faster. And what this means is the difference between y values is increasing as the x values increase. So basically, x plus 2 squared minus x plus 1 squared is greater than x plus 1 squared minus x squared. So when x is 10, 10 squared minus 9 squared is greater than 9 squared minus 8 squared, which makes sense. You can see this curve get steeper and steeper as it's getting further from 0. So the derivative is really just the slope of the function, which you can see here. The derivative is the slope of the function, but at a single point. So we take the derivative at a single point. And one way to calculate the derivative is called the finite differences method, which is basically just taking y values and subtracting them and dividing them by x values. So we can graph that out to find the derivative of x at 5. So we find 2 points really, really close to 5. So 5 minus a very small number and 5 plus a very small number. These will be our x values. Then we find the corresponding y values. So just x1 squared and x2 squared. And then we calculate the slope between those points. And this gives us the derivative at 5. So the derivative you can think of as if I add a very tiny amount to x and subtract a very tiny amount from x, what's the slope between those 2 points? So what we say is the derivative at 5 equals 10. Or in math, we would say this. F prime of 5 equals 10. So the rate of change of the function x squared at x equals 5 is 10. And we can go ahead and plot this derivative. And it just looks like a line, right? As x gets bigger, the derivative also gets bigger. So this means that the rate of change of the function increases as x gets bigger. So a couple of things to note. Derivatives are very, very important for training neural networks. They're how we do backpropagation and how we update the parameters of neural networks, which we'll learn about later. You don't need to derive the equations yourself usually, since you'll be given them beforehand. But in a later lesson, we'll learn how you can break the derivative of a complex function into pieces and then solve it on your own. All right, so that was a very quick, very basic intro to the math you'll need for deep learning. In the next lesson, we'll actually learn how to use gradient descent to calculate the w and b values and figure out the correct coefficients for linear regression. All right, I hope to see you in the next lesson.